So, a manufacturing facility is filling up soda cans, and they're asking us, in part A, they're asking us for the mass flow rate. So, the mass flow rate can be defined as the density of whatever the liquid this is. In this case, soda. However, soda is made mostly of water, so we're going to use the density of water for this one. So, there'll be density of water times the volume flow rate. Now, the volume flow rate is much easier to calculate. Rather, it is you need to find the volume flow rate before you find the mass flow rate. So in order to solve part A, we should solve part B first. So the volume flow rate needs to be in meters cubed per second. And they're helping us out in the sense that they're telling us that they're filling 220 cans, and then it's 0.355 liters per can. And then this is happening every 1 minute. And of course, in every minute, there is 60 seconds. So from this, we can say that the volume flow rate is going to be 1.30 liters per second. Now, we should try to convert this. So for every 1 liter, for every 1 meter cubed, there are 1,000 liters. So this volume flow rate actually becomes the volume flow rate is actually this number divided by 1,000. So it would be 1.3 times 10 to the negative third meters cubed per second. At this point, we can now find the mass flow rate. So if this is the answer for part B, part A is going to simply be the volume flow rate times the density of water. This would be 1,000 kilograms per meter cubed times 1.3 times 10 to the negative third meters cubed per second. And we find that the mass flow rate is going to be 1.30 kilograms per second. So this would be the mass flow rate. Now, it's asking us what is the speed of this of this soda in the first section of the pipe. And we can say that the cross-sectional area times the velocity is going to equal the volume flow rate. This makes sense. The cross-sectional area is meters squared. The velocity is going to be meters per second. And of course, that'll give us a meters cubed per second. So dimensionally, this makes sense. At this point, we can say that the cross-sectional area, A1, is going to be 2 centimeters squared. Now, for every 1 meter squared, there are 10,000 centimeters squared. So when we solve for this, we're actually going to have to say that V1 is going to equal the volume flow rate, 1.3 times 10 to the negative third meters cubed per second. And then this is going to be divided by 2 times 10 to the negative fourth meters squared. And we find that the velocity in the first section is going to be 6.5 meters per second. So for the first 3 parts, the volume flow rate is what helps us the most. We find the volume flow rate first, convert it to meters cubed per second, multiply by the density of water to find the mass flow rate, and then we use the volume flow rate with the equation of continuity in order to find that the velocity in that first section is going to be 6.5 meters per second. Now, the second part of the problem asks us to find the gauge pressure in the first section. Now, we need to use Bernoulli's equation for this. Bernoulli's equation simply models the conservation of energy of flowing liquids. So here we can say that the gauge pressure plus half times the density times the velocity in that first section squared plus the density times the acceleration due to gravity times the height of the first section is going to equal a constant. If this is constant throughout the entire pipe, we can simply define another section of the pipe, P sub 2 plus half density V sub 2 squared plus density acceleration due to gravity H sub 2. Now we have the first, this is what we're trying to find here. So we have the second pressure, we have the density of water, and we have the velocity in the first section, and we have the delta H being 1.35. Now here, what we're missing, however, is this right here, this V sub 2. So we're going to use the equation of continuity once again. And we can say that V sub 2 is simply equal to A sub 1 V sub 1 divided by A sub 2. This is, now everything is, we can use centimeters squared because we're simply dividing, and that means that the units are not really going to matter too much. So here it would be A sub 1, we could say this is 2 centimeters squared, and then it would be times that 6.5 that we found earlier, divided by the cross-sectional area of that second section, 8 centimeters squared. This is going to give us 1.625 meters per second. Now we have to solve for P sub 1. So P sub 1 could equal P sub 2 plus half times the density of V sub 2 squared minus V sub 1 squared plus the density times the acceleration due to gravity of H sub 2 minus H sub 1. Now, notice that the second section of the pipe is actually lower than the first section of the pipe, which means that this term right here is going to actually be negative 1.35 meters. So this is extremely important. You have to recognize that the second section is lower than the first section, which means that the difference in this scenario is going to be negative 1.35 meters instead of a positive 1.35 meters. So solving for this, and we have the pressure sub 2 is going to be 152,000 pascals, or 152 kilopascals, plus half the density of water, 1,000 kilograms per cubic meter. Velocity, the velocity in the second section squared, 1.625 squared minus 6.5 squared. So again, you can see here that this is going to result in a negative number. And then we have plus the 1,000 times the acceleration due to gravity. And then, of course, again, remember, it's going to be negative negative 1.35, I apologize, meters. So once we have this, we can simply substitute in. And again, you see that this term right here is going to be negative. This term right here is going to be negative. So the pressure in the first section should be less than the pressure in the second section. And solving this out, we find that the pressure in the first section is going to be 118,965.3125 pascals. We can round and say that this is going to be around 119 kilopascals. So this would be the final answer for part D. So part D was definitely the hardest part of this question, in the sense that we have to recognize that we need to use Bernoulli's equation in order to model the conservation of energy for flowing fluids, and then recognize that the height in the second section of the pipe is actually lower than the height in the first section. So this difference right here is actually going to be negative. And we end up with, again, 119 kilopascals. And that's the end of the solution. Thank you for watching.